just to recap, a van der Waals force, okay, is, so if we have a molecule of carbon dioxide and another molecule of carbon dioxide, okay, the force between those two is called a van der Waals force. So there is some minor attraction between the two molecules because both molecules have positive and negative bits. So there's minor attraction between the two molecules, and that's a van der Waals force. It is very, very weak. Yes?
Yep.
Now that's why carbon dioxide is a gas at room temperature, because that force is so weak. Water, however, is liquid at room temperature because those forces are much stronger. The reason those forces are much stronger is because in water we have a special type of van der Waals force. We have polar bonding. So, what is polar bonding? Well, what happens in a water molecule is that they happen to have this strange geometry where it's not just an oxygen and then a hydrogen here and a hydrogen here. The hydrogens actually sort of have like 60 degrees between them. So we've got an oxygen, I know the diagram's right there, but you know, here's another one. And a hydrogen and a hydrogen. Okay, so they kind of, the molecule ends up looking like this. Okay? Now, oxygen is relatively electronegative, which is not really a word I want you to worry too much about. What it means, though, is that oxygen is quite good at attracting electrons. Hydrogen is not so good at attracting electrons. So, because what's happening here is this covalent bond, they're sharing electrons, right? So, what this line really is the sharing of two electrons, isn't it? Okay? Now, because oxygen is slightly better at attracting electrons than hydrogen, we end up with the electrons being slightly closer to the oxygen than to the hydrogen. Yeah? Yeah. Now, that gives this end of the molecule a partial negative charge. It's relatively negative because the electrons are all up this end. So to write a partial negative charge, we use this symbol. Okay? Partial negative charge up this end of the molecule. Down this end of the molecule, we have a partial positive charge. Okay? Because the electrons are over that way. So we have a partial positive charge up this end. Does that make sense? Okay, I just want to see if there's a nice diagram on the next slide, and yes, there is. Did you want to copy down that diagram? Yeah. I'll just give you a second to do that before I look at the next one. Are we good? No? Okay. Just one second. Why are you whispering?
I don't know. Change the colour back.
Okay.
Just invert his
Now, what this does is it makes the attraction between the molecules stronger. So if we look at this diagram here, we know that our oxygen here has a partial negative charge. Our hydrogen here has a partial positive charge. So the electrostatic attraction between our partially positive and our partially negative is stronger than if they weren't partially positive and partially negative. Does that make sense? So we get electrostatic attraction between the oxygens and the hydrogens from other molecules because of those partial charges. This electrostatic attraction is called a polar bond. Okay? So that is a polar bond. And it's between partially charged atoms, effectively, within molecules. So, for polar bonds, they're not a huge part of the course. You only need to know about polar bonds with respect to water. You can't get asked about polar bonds for any other type of molecule, only water. So that might help a little bit because you don't have to think about other elements and stuff. All right, next slide. Yep, we talked about that. They have higher melting and boiling points, which, like I said, is why water is liquid at room temperature rather than a gas. Because those bonds are stronger, so they're closer together, making it a liquid. On to the next topic. So, we know that covalent bonds are really, really strong, right? Yes? Covalent molecular substances have weak forces between the molecules, right? But then we also get these substances that are made up of just covalent bonds throughout the whole substance. So as you can probably imagine, that would be super, super, super strong with a really, really, really high melting point. Okay? So there's two different types of covalent compounds. One is covalent molecular, which is where we have our van der Waals forces between molecules. The other is covalent network, which is just one big thing full of covalent bonds only. Okay, so we're going to have a look at what the structure is going to look like in a minute. You need to remember these substances, okay? So when you get a covalent substance, you know it's covalent because it's two non-metals, right? How to know whether it's covalent molecular or covalent network is just based on your memory. Okay, so which ones form covalent network? Anything with silicon in it, okay? If you see silicon anywhere, it's going to be covalent network. So remember, silicon compounds are covalent network, including silicon by itself. The only other one you have to remember, other two you have to remember, is boron by itself is covalent network, and carbon by itself is covalent network. We look at two different ways that carbon can bond. It can bond to form diamond, and it can bond to form graphite. Okay, we know what diamond is. Do we know what graphite is? Yeah, in your pencils, yeah. And I also, when I was setting up that cell up the back the other day, and you know how I put those black rods in the solution? So they're graphite as well. So graphite isn't always weak like a pencil, but yeah, that's graphite. Very, very, very high melting points. So that's what we need to remember. Silicon, carbon, boron, covalent network. Now, carbon's only covalent network if it's by itself, yes? If we have carbon dioxide, for example, that's very clearly not covalent network. All right. Here is an example of what it might look like. So this is silicon dioxide, which is sand. So the way that the structure works is so each silicon is bonded to 4 oxygens, and each oxygen is bonded to 2 silicons. And it's continuous, okay? So these are all covalent bonds, and they're throughout the entire lattice. So it's like one really big molecule, yeah? So we call it a macromolecule. Now, we give it the form, so we write it as SiO2. I don't know why I've written it when I've just circled it as well, but whatever. That doesn't mean that we've got molecules of 1 silicon and 2 oxygens. It's telling us the ratio of the macromolecule. And the ratio is that for every silicon we have 2 oxygens. Does that make sense? Any questions? Okay, diamond and graphite are carbon structures. They are covalent network. They are made up of continuous covalent bonds, but they're really different. So they're both just carbon, but they're really different, but they're really interesting, yes?
If this is like a continuous network, how does
It must...
Something the government isn't telling us.
It must, like, I don't know, like maybe this bond, instead of going to another carbon, it bonds to that one. Why not, hey? Why not? I don't know. Sorry. But you're never going to get that question on an exam, so don't worry about it. All right. Now, where was I?
So people watch the live feed, comments the answer.
He might have to Google it first. He'll be like, yes, I pretend I know, like I'm going to pretend I know this. Sorry, guys.
That's the strap. Like in a Skype call, you pause your webcam real quick and Google the answer.
Anyways, we digress. Okay, shh, Finley, you shush now. Now, diamond is so strong. We know diamonds are strong. We love diamonds. They're beautiful. Every carbon is bonded to 4 other carbons. That's it. This makes sense because carbon has 4 unpaired electrons, so it can form 4 bonds. So every carbon is bonded to 4 other carbons. Correct? Yes? I mean, it is correct. What?
This one is not.
This one is.
All of them are bonded to 4.
They just couldn't be bothered drawing the entire thing. But that's what's happening. Now, graphite is amazing. Okay?
Is it stronger?
No, it is not stronger. It is weaker.
That's how
You guys, shh. This is not good for my live stream. Okay.
Oh, she's worried about the mic.
Graphite is stronger because every carbon is bonded to... Not stronger. What?
Now you've messed up your live stream.
Graphite is weaker than diamond. Yes, listen. Because every carbon is bonded to 3 other carbons, okay? In a 2-dimensional layer. Yes? Bonded to 3 others in a 2-dimensional layer. Yes.
Isn't that why it conducts electricity?
Yes, because... Yeah, go on.
Oh, well, go on. Doing layers so that electrons can go in between them.
Yeah, what electrons?
If you're running a current.
Huh?
If you're running a current through it.
I mean, yeah. You almost got the whole answer that I like.
Thank you.
Yes. Because... No, I am impressed, to be fair.
You know we're on a live, right?
It's fine. Everybody who's watching already knows me. Although there are some people in the Facebook group now that are not in my class. They'll be like, who is this person? Okay. So we know that carbon has 4 unpaired electrons. If it only bonds to 3 other carbons, what happens to my last unpaired electron? It starts with a D. Delocalized. It gets delocalized. So every carbon atom releases an electron. It becomes delocalized. So in between my layers of graphite, I've got lots and lots. Shh. You ruined my audio quality. I've got lots and lots of delocalized electrons. So graphite can conduct electricity. If I apply a current here, it's going to push the electrons along. They'll go out the other side. We get electricity. It doesn't conduct electricity as well as a metal because the electrons can only go between the layers, not through the layers. Do you understand?
Yes.
Okay. Now guess what the chemical symbol for carbon is? Guess what the chemical symbol for diamond is? C. What about for graphite? No numbers. They're both just C. Solid if you like. We could annotate. We like annotating. Alright. And we've got one more slide. And then we can do questions and turn off the live stream. So, here we go. Here is a summary of the properties So, covalent network. We know covalent network generally does not conduct electricity. The only exception is graphite. It doesn't conduct electricity because there are no delocalized electrons. Yes. It has very high melting points because it's made up of covalent bonds and they are very, very strong. They're very hard, same reason. They're brittle, same reason. If you smash them, then you're just breaking those covalent bonds. No